Start recording. Okie dokie. So we've just done a whole bunch of setup, and so here's the canvas from last week. So, right, you remember last week we were looking at this, I don't actually want to draw on canvas 8, but we were looking at this, here's the x basis vector and here's the y basis vector. And yeah, we were just having a quick discussion about what we do with the basis vectors. So, and what we wanted to do actually, based on last week, was we wanted to do this business where we multiply two matrices to get the transform out. So,
yeah, quick thing though, that the three blue, one brown, just because I just watched it, right? So I have the benefit of immediate hindsight. I just noticed that you drew in he's the I hat and J hat are landing vertically, whereas where you drew those green and red boxes, they were horizontal.
Yeah. So
are we in a different coordinate system?
So do you remember what we talked about sort of at the start of last time? It's like we can do this in the sort of graphicsy way or the sort of
yes,
mathsy
I remember.
Way. So
that's right, and he's doing it the mathsy way. But
he's doing it the mathsy way. So in his case, which one am I drawing on? It's like there's his x, and I think I have the colors reversed now, but yeah, there's this y basis vector. So j hat and I hat are those ones in the maths version. So that's basically the only difference, and it all works out the same. And you put the vector you're transforming at the end, whereas in this one you put it at the start.
Right. Okay. Yeah. Because in his, he was transformations are going right to left as well. I'm not sure if that's going to change for us.
Yes. Yeah, they do go right to left as well. Pretty much.
Okay. Cool.
For the same reason as just the single vector transform goes that way. Okay. So what I wanted to quickly, I just want to, and for those people watching at home, here's the thing that we're talking about is this Essence of Linear Algebra video chapters 3 and 4, which sort of cover this as well and have nice interactive animated diagrams. So I'm just going to cover these really quickly because Daniel's already watched those and I've already watched those, and you can watch them at home too. So you remember last week we had our thing and we're like, right, here's our x. I'll draw that fairly small. This is going to be x hat, and here's going to be y hat. So this is just, that should just be sort of fairly straightforward. Here's 1, here's -1, here's 1, here's -1, and then we want to do a 45-degree rotation. So and we did that thing where we scaled up to square root of 2 equals 1.4 blah blah blah, because it just makes the maths easier if we say this is 1, this is -1, this is that, and we just go and we're going to say this is our new coordinate system with our basis vector I hat, and this is going to be j hat, which is, and these map onto x and y, obviously. So that should be sort of straightforward to you so far, and everything we covered already. And then we had a vector, I think it was 1, 2, and we're like, well, let's transform this vector. And so it's going to be, 1 on the x-axis and 2 on the y-axis. And we see that when we try and do this vector, represent this vector, we take the basis vector y hat and we go, 2 on y hat, and we go from there, we go do up to here, we're there, and then we go, and obviously it works in the other order as well, we can 1 on the x-axis, so 1 of x hat. We've just added basically this vector v equals 1 x hat plus 2y hat. And so if we do a transform, we're doing basically the same thing over here. So if we transform it by this matrix, which we determined the other day was a rotation matrix that looked like, you remember this is cos, so let me just do it up here, cos sine neg sine cos of theta, and theta is 45 degrees, and this ends up being 1, 1, neg 1. I don't want that phone call.
That was terrifying.
I love my ringtone. It's pretty funny, but it's also like the worst possible time for them to call. Okay, so this is our thing, and you remember that, like, okay, we have our basis vectors. There's I hat, and here is j hat. So we have, -1 on the x-axis and on the y-axis. So then when we go to transform our vector, we can do the matrix multiplication and be like 1, 2, and multiply that through equals blah. And we can do this geometrically and go 2 up on the on the j hat, and 1 plus 1 I hat, and we end up with this vector we had before rotated 45 degrees. So if the old one was out there, more or less, if we've drawn this accurately, this is like 45 degrees. Okay, so what I wanted to cover in that case was what happens if we that's right, and then we said that this ended up being, and we did the maths for this, and we're like, well, that's 3 neg 1, so that's neg 1 and 3. So what happens if we wanted to combine these operations, like we wanted to do, for instance, a rotation and a scale, and then maybe another. I'm gonna say, why don't we do this one again? So why don't we say that what we're going to do is 1, 2, 1, 1 neg 1, 1, and then 1, 1 neg 1, 1. That's 2 operations. What's that going to equal to? And so what we have is we're sort of doing this same operation again. And so this time we have, we've done it once to go from 1, 2 to neg 1, 3. So let's use pink for this. So we have neg 1, 2, 3. So we have this vector here.
Mm-hmm.
And that's neg 1, 3. And now we want to apply this. So we want to take neg 1 of this green one, so negative I, and 3 of the j hat. So 1, 2, 3. Is that right? No, I just sort of drawn that really badly. Because it's like there. So there's 1, there's 2, and 3 would be up about here. And so the result of that transform ends up being a vector here. And as you can see, we've scaled it up again. So you can see it goes 1, 2, 3, and it's also rotated around another 45 degrees. So hopefully does that make sense geometrically, what we've done?
Yeah, but I don't, unless it's just, and forgive me, unless it's just bad drawing. The pink didn't also scale, right? We've only applied the rotation matrix twice. So we didn't scale it, right?
So we've scaled it up by this 1.4 whatever 1.41 whatever factor. So you remember
where is that represented in 1 1 neg 1 1? Just because of the cosine thing,
just because the cosine of cos of 45 degrees is actually like, I think it's 0.8 or something.
Right. Okay, that makes sense. Yeah, I just forgot that it's sort of embedded in the rotation matrix. It's not. It's not perfect because rotation can't be perfect because it's on a circle, right?
Exactly. So and once we never mind the very loud truck. Once we get it into the code, we'll be able to just see it working as we like. So we want to do this operation here. We want to now combine those two. So we've done it once, and then we went back and we did it twice. We want to combine this. How do we do that? And you'll recall that we had this situation where we went across the rows and down the columns. So we know, and we also have, you recall, we have a 2 by 2 matrix and a 2 by 2 matrix, and we end up with a 2 by 2 matrix at the output. So we can just go right there. And so 1 times 1 plus 1 times -1. And it's like, okay. I'm going to just write this one out because
don't worry.
Minus 1 times 1. Okay, and then the next one is 1 times 1 plus 1 times 1. So that's 1 times 1 plus 1 times 1. This one is, then we're going across here for the lower one, and this one here, so -1 times 1 plus 1 times -1 times -1. And all of these ones are starting to get a little bit confusing, but that's fine. -1 times 1 plus 1 times 1. 1 times 1. And let's then go and try and slap that together. So that's 1 plus -1 is 0. Is that right?
Well, 1 plus -1 is 0. Right?
I feel like that must be right. That's cool. If I've made terrible maths errors, then
that's fine.
This is what.
Yeah, that one's 2.
This one's 2. This one is -1 plus -1, so that should be -2.
Yeah, and that one's -1 plus 1, which is 0.
Yes. So that makes that is actually makes a lot of sense. So we end up with
I mean, it's
this, and we have we have our basis vectors. This is would have been the combined I hat, and this is the combined j hat. So we'll draw those out, and we'll say so if that is 1, that is 2. Okay, and so what do we have? We have green, so this is our new I hat. And this is making sense because we've rotated 45 degrees and then 45 degrees, so we've come out a total of 90 degrees. And we've scaled up by square root of 2 times square root of 2, so we're expecting to have a total scale of 2, which we have. And then we have -2 that, so we're now going that way. Okay, and then let's apply that to our original vector here. So we have 1 of the x, and so this is actually making perfect sense. So
we're applying it to our basis vector, or are we applying it to the transform vector after the one? Yeah, after the 1, 2.
So we're now taking this and applying it. We're applying this transform, so the combined transform.
Yeah. Sure.
So 1 and 2, and so we've got 2 of the j hat and 1 of the I hat, and then we end up here, and I think I was doing this in pink just for congruency, and it ends up here. And if we look at these two diagrams, even though I've sort of scratched them out fairly roughly, you'll notice that they're pretty much match. So that's sort of geometrically and mathematically how we implement multiplication of transform matrices, and sort of the fact that they work. And so we end up with new basis vectors that encode like the two transforms we're doing, even though they're both.
I have a GPU / compiler question.
Yes.
Well, okay, so you just took these two rotations and you composed them together, but which makes sense from a code point of view, like, you know, does it make sense to take the two rotation, like matrix 2D dot create rotation, the two of them that you have there that are independent? Should we always smash those together before passing to sprite batch, or is this the kind of thing where it's premature optimization and like it's almost already built in? Okay,
so like this is one sort of reason you do this is it's a good optimization. So rather than being like, right, well, I want, you know, in this case I want a rotation, I just pretend it's a rotation. Yeah, create rotation, and then create rotation. I've got you know, I've got 4 times floating point values and 4 times floating point value, and so now I have like twice as much memory. And if I have a function like, you know, line, you know, I don't know how I'm going to actually do this. Like suddenly I need like, well, here's a rotation, here's a scale, and like if you're doing sprite batch.draw, they actually do this a bit because it takes, you know, rotation and scale and origin and all this other stuff, and then produces these matrices, and it collapses the mass down into a single step. I mean, I expect it does. Like, I'm not sure you've seen the code for this, if it's actually in River City or not. But there's a case where, you know, if I want to create. I don't know if this method is in River City, but I have my own method in one of my own bits of code that's like create, translate, scale, rotate, translate, and it takes all of those and it does the maths in the most shortcutty way possible to collapse it down. But the thing is, once you collapse it down, like, you now have only 4 floats, and you don't have to do all of the multiplication that was involved in doing the collapse.
But wouldn't you still have to cache that though? I mean, your create TSRT method would still be called every time unless you would have to cache that somewhere.
Well, exactly. So, because what I was about to say is like, the odds that you're going to draw no, you're right. But the odds you're going to draw one line is pretty low. You're probably going to go line and line and line and line and line, and so the fact that you can make that one single matrix that you just pass in again and again and again saves a whole bunch of performance, because you're not having to go that and then get the result. You're just going that to like the group and get the result.
Right. Well, you would have composed all 3 of those with yours. Like, you would basically figure out the smallest matrix you can get and then blast it in there. But I guess it's weird to me because, like, you know, sprite batch takes that kind of matrix 2D overload.
The beginning,
which is method. Like after you've done, and I guess because I'm wondering if that's useful or not, because after you've done, you know, the baked version of scale and rotate and origin and whatnot, then it's going to apply that one that you pass it. But it sounds like you almost want to avoid that and do it all up front yourself.
Well, the thing with this one, and this is getting into something, so the 3D equivalent of this is the 3D equivalent of this is you have a model matrix, a view matrix, and a projection matrix. And so the model matrix, you know, you've got like, you know, you've got your ogre or something, and it's like based around its origin as, let's say it's at its feet, and you want to put that into the world. So you've maybe got a scene, you got some like I don't know, ogre houses or something, and the origin of this world might be like here, and you want to place your ogre like, I don't know, just next to his house, and so so this and maybe like the scale is wrong, so you've actually like, this is a massive model or something, and so if that's like 1 unit, you want to scale that down to like 1 unit or something, and so that would be your like that transform that gets you there from like model space to world space is the model matrix. And then you have the view matrix, which is sort of like the camera. It's like, right, well, I'm actually over here looking at this house. In fact, that's actually a confusing way to draw it because of what's coming next. I might be here looking at this house, and so what the view matrix does is it basically transforms the entire world around, so that it's sort of such that it's in front of the origin. Like I'm not sure that's a really great way to explain it, but it transforms the entire world around, everything in the world, such that it's in the right place so you can see it.
Right. Yeah. Sorry, I conflated it with some kind of overload for the actual drawing itself. But no, that's the one in the beginning. And I remember that's usually for like viewports and whatnot. So that makes.
So
but wasn't there a matrix that we talked about last time that was difficult? Is that the transform one? Because we've only done scale, rotate, and translate right now.
So I want to get to translate this lesson because
cool.
It's not too tricky. It's just a little bit different. So yeah, the projection matrix just takes whatever's in this. Like say I'm looking at this house, it's going to be sort of in this view frustum, and it sort of takes that and compresses it into like this, I guess a square that is the screen more or less with, and this is confusing because it doesn't actually because this is not sort of spatial, but also has like depth to it. So it's like if a thing is there, it ends up there. If it's way behind that, it's like outside of it's behind the far plane, for example. And so and because it expands out like that, that's how you get perspective. So things that are further away end up smaller than like the same thing up here would end up bigger, because it's obviously the frustum, this sort of cut off, not quite cone, but you know what I mean. It gets smaller. So anyway, if you're drawing a lot of sprites, the rotation scale stuff is equivalent to the model matrix, and so the thing is like, which is the one that puts it in the world. So if you were to have the same one for every sprite, you'd basically have every single sprite would be laid over the top of each other. So you necessarily have to have a different model matrix. Different model matrix for each sprite, just so they're not all overlapping each other.
Right.
And then the view matrix, this view matrix is what goes into begin, and it's like sort of placing the camera. So it's a transform that's applied to every single one of these, and so you might end up equivalently having a camera like that covers those ones. Make sense?
Yep.
Yeah, and then the projection matrix is just the orthographic matrix that takes that, which is, this is 0, 0, and that's like width, height of the screen, or, however that does it, and it shoves it into the space that gets used by the GPU in the same way that this does it for 3D. And this is built in.
Yeah, I'm just going to say we don't have anything to do with that, especially with our 2D stuff.
Yes. So so that's sort of why draw is the way it is. But what you find is like when you're doing like a shader, if you're drawing a single model, this will be made up of a whole lot of vectors, and the GPU has to go ahead and transform every single one of those vectors So what ends up usually happening is you take all of these and you multiply them together to get a single matrix that you pass to the shader. And so often that's called like the model view project matrix. And so in 3D, that's how it's done. If you're drawing a single model, if you're drawing like the same model multiple times, like we have several different ogres, it gets a little bit more complicated because you do like instancing and stuff, which we won't go into too much detail, but yeah, it sort of just does that, and then you have many different model matrices. So hopefully,
I didn't realize the reusability of models happens at that level too. You don't just like for each and keep drawing the same ogre. You actually pass multiple models in.
Yeah, so you pass in a single, I guess, vertex cloud. I don't want to say a model because, about a 3D model, which is made up of vertices, and then, n times these matrices. More or less, like it depends what you want to change about the instances. Like maybe you want to change the color and stuff, so you have some more stuff as well that goes in. But yeah, so that's how that works in 3D.
Cool.
Let's talk about how we actually do the multiplication. So, because we want to go over to implementation now. So let's quickly run through just make sure we have our maths right. So we have M00, M 01, M10, M11, and we have our next matrix, and that is N00, N01, N10, and N11, and then we have to go across and then down. So that would be, so the first one would be M00 times N00 plus M01 times N down 10. So this is gonna get fun. Let's quickly just go through all of these just to make sure we have it all down, and we can just bang this into the compiler. So the next one would be, actually, let's start writing code, because maybe we can just do this in the IDE. So have you got your coding stuff ready to go? So let's make.
I've been muted the whole time. I've been having a wonderful conversation with you.
Oh, sorry.
Yeah, no, it's fine. We're good. I was actually going through and doing the Mu, Mio, M stuff, but now we don't have to. But yes, my coding stuff is here and ready. So.
Okay, so let's make a new operator, and okay, so static matrix 2D operator multiply I'm going to call them A and B actually. Let's go bring this
not
up.
Going to compile. I think you're missing explicit or implicit or something.
Oh no, I don't need implicit. Implicit isn't implicit for construction. I don't know.
Forget. But it will compile that way.
It will.
It will.
It will.
Sorry.
Yeah, no, it's
super helpful method.
Look, I'm going to be honest. I have the window up here for the documentation for how to overload an operator because I do it so rarely.
Yeah, I always forget too. I'm missing one or two things. But yeah, this is
okay.
This is the easy one.
So R can be our result, and M00 so equals. So we go across for the A and down for the B. So
it's M00 plus B M10, right? And then and then M01 is equals to for it's a little harder to visualize here, but so
what you'll notice I've moved this right up to the top, and you remember last week I did this little trick where I'm like, let's lay these out graphically so I can see.
Yeah, they look. Yeah, I'm just gonna cut those and bring them down to my.
Yeah. Yeah, I did the same thing, only backwards. Okay, so and if we get it wrong, then it will look very silly.
I'm already thinking it's wrong. But M00 M00 plus B M times B's M00, isn't that supposed to be times BM10? Because they're going down? Or am I confusing myself?
Hang on. So B should be going down and A should be going across. So
yeah. That's right. Are you gonna do one of your famous ASCII arts?
Oh yeah. So the first one will be A00, B00, A01, B10. And so the top corner is the easy one. 01 equals. So that becomes 01 and 11. And that becomes that's now the lower one on that, which is that, and then that.
This is not my favorite thing.
No, I'm not a fan of having to do this, but one neat trick is check that you have like 4 of them and they look sort of geometrically,
right.
four of each, and then if they look geometrically useful, that sort of helps.
Yeah, just because we were actually doing them kind of not the way we did them before. We're kind of doing each component like we're not doing one at a time. We're doing them kind of interleaved together, which hurts me.
So let's okay. So you got that one. Now let's do a little bit of this business. Just so we are making sure we are good. So I'm just going to make a identity matrix.
That one's easy.
So that one's really simple.
What's going on? Oh. Typing stuff in. Let's go. Not enough?
Yes. I was like, does C# work like that? Yeah, it does.
Value text. All right. Structs.
So okay. I will give you a little hint though about this sort of a nice way to do things in C#. If you make a struct like this, and then set every member, and then like return it. If you were to go ahead and be like public float bar and hit build, all of a sudden you get all these compiler errors. Use of unassigned local variable, because you haven't completed the construction of it, and obviously those will go away if I go
right.
new like that, like you'll see that wiggly line will go away. But if you don't initialize it like that, you tell the compiler, right, I don't need you to call the constructor. I'm going to set every single field myself.
Oh, I see.
And so if you go and add a field, you'll actually get compiler errors. So that's sort of a neat little trick.
That just forces you to cover the layout.
And
less errors.
Yeah, that one has helped a few times in my experience. You'll notice that, like I code like this. You'll have seen that sort of pattern in River City a few times, and it's helped because it's like, all right, I need to add something to this struct, so I add it, and there's like, bam, all of these compiler errors. It's like, right, there's all the bits where I need to not only fix, but I have to like think about what that added member should be. So that's handy. Sense. Okay, so
I have used it to make it visual, which I would never do in real life, like kind of stack left to right.
Oh, this is nice. Like
I wouldn't do that.
The thing about code is like you write it once, but you have to read it again and again. So anything you can do to make it more readable, or like that other thing I was saying, like to make it fail in useful ways when you change it.
Right.
Those are good. You want to do as much of that as possible, more or less. So what you've done there, like that's fine. Do that. Do more of that. And like this business with the ASCII art, sort of.
Right.
This is a really mild example, but yeah.
Oh, I just remember when we were talking about extrusion of height map instructions. That's definitely where you want to be like, okay.
Yeah. Okay, so let's head up to our draw function where we've got all this fun stuff going on.
Right.
Let's just run it. So you'll notice I've slapped in something a little bit fun. If I go here, and I was just mucking around with this before we started, if I go here and change that, all of a sudden, you'll just have to wait for it. Way! We've got this spinning thing. And that's kind of cool. It sort of shows that it's actually working. So let's try some things. Let's comment that out for now. Let's make some new matrices. So 2D foo equals okay, so we're going to matrix 2D dot create rotation, and I think 0.2 was useful, and then times matrix 2D dot create scale, and let's scale that by 1.5, and then what have I done differently? This create scale has invalid arguments.
It's plug F.
Yeah, and I've gone and used the built-in one. So what I'm going to do is I'm going to reverse these arguments, because I'm not sure we actually mentioned this, but they talk about it in the 3 blue 1 brown video, and that is that matrix multiplication obviously is not, I've forgotten the name for this.
Commutative?
Yes, I think that sounds good. I like it, but you know exactly what I mean.
Yeah, order matters, and you're going to
the order matters.
In the wrong order. You're going to get something different.
Let's try them in different orders, and let's replace that with foo and bar. So foo is green and bar is blue, and let's see what happens. Okay, so we've lost bar. Let's figure out where that is. Maybe we'll rotate around the other way.
We lost foo. At least mine.
Yes, we've lost foo. Why? So now it's up to us to figure out why we've lost foo. And
well, bar is visible and foo is the, well, it's not the inverse, but yeah.
Hang on.
State of dry.
They are the same. Yeah, they are the same.
Yeah, vectors, so it's,
I was triple checking that everything's actually drawing. Yeah, okay. So, I'm stupid. Not that stupid, but
you draw them on top of each other?
we've drawn them on top of each other is basically it. And if I change the order, yeah, it's fine. Everything is fine. We're, professional coders here. Because what you'll find is that if you scale and then rotate something, it's the same. But what I want to do now is let's make our scaling matrix. The first one, let's scale it up by 1 on x each time. And I think, yeah, in this case, you'll notice we get a different result. And in fact, what I'm going to do is now, what do I want to do? Have a quick think about that. Yeah. So what I'm going to do is I'm going to bring our good buddy theta back.
Mine is weird.
Sorry, let me look at yours.
I think just
have you put the rotation in the right in the same thing? Let me back out that change and be the same as yours, because if we are different, we might have a small issue. Yeah, no, it's fine. I just did negative 0.2 on the rotation.
Oh, okay. Yeah, okay.
Which ends up with that. So that's fine. So what I'm going to do, let's put theta back in these things and animate. So you can see that.
Oh.
Yeah, you want total because
right,
it elapses per frame. Yeah.
Yeah. Right. Oh, good.
Oh, you want it for both of them. So
sweet.
Cool. And just wait for those to spin around. Here they come, and you'll notice that they are different, and that's because on one we're doing the scale first and then the rotation, and the other one we're doing the rotation and then the scale. And what that means,
last time.
Yeah.
Right.
I was going to
say last time we picked unlucky values. That's the only reason it didn't work.
Well, we picked values that were uniform scales.
Yes.
But this sort of becomes particularly interesting. Like this one's. Let me see if we can draw it out on the whiteboard. This one. So. Yeah, let's see. So if we have just a simple vector, okay, I've hit some buttons and everything is broken. Okay, so if we have a vector that's like this, and we rotate it, and we scale it up. In fact, why don't we, yeah, we'll say, I've done 0.15 there, just because it's easy, but I could do 2 just as easily. And maybe that will show off the example better. I was keeping the scales sort of shorter so they would actually fit on the screen. But so say we're scaling up by 2 on the x-axis, and 1 on the y-axis. I think, is that what I did? I did 2 on the y-axis. So So if we rotate 45 degrees and then scale it, we rotate there, and then we scale it up by 2, we end up here. So we've rotated and then we've scaled. So that was the intermediary. And we'll do the other one in sort of pink and red. So we'll scale it. So we go up by 2, we're there. And then we rotate it. We end up up here. And because it's 45 degrees and the scale is the same, we actually, it's more or less the same, but you see there's already that difference there. And so you can imagine if I picked values that weren't quite so, like 45 degrees is sort of ends up in situations that are like that, and this is, this is 45 degrees, sorry. And this is just a consequence of picking those kind of values. It doesn't actually change much, and you can imagine that when you start adding translation in, so let's say we have this horrible axes. Let's say we have a thing that's like a happy face, and we wanted to translate it, say 1, 2, 3 over here, and then scale it by 2. If we translate it to there and scale it by 2, it ends up, 1, 2, 3, 4, 5, 6, and twice as big. Whereas if we had scaled it by 2, it will scale by 2 and end up like that, and then we translate it by 3. It ends up still twice as big, but it ends up here.
Right.
And so if we'd rotated it and then scaled it, if we'd rotated it 90 degrees, we'd end up, I'm running out of colors, we'd end up with this, and then translate it, we'd end up with like that. We'd end up with that. Whereas if we'd translated it over here and then rotated it 90 degrees, it would end up, up here like that. So it would be that red one and then come up here. So that sort of just shows geometrically that order matters. So let's, so what we've been doing up to this point is, I'm just like, what's the correct term for that? It's linear transformation.
Right. Linear transformation meaning everything is parallel and there's no squigglies.
Exactly. Get my paintbrush back. Okay, so if we want to add in translation, we now have what's called Affine. A-F-F-I-N-E. Affine transformation. So
I've heard that term before when discussing like trying to correct an image based on like its angles or whatever, so that you can kind of like normalize pictures of things that you see in it, even if they're taken at weird angles. I don't know if that's even what we
well. So let's talk about what affine transformation is. I'm just deciding where to start, because it's like you remember last time we went through like different ways of representing it and all sort of came together. I'm like, which one should we start with? And I think what we'll start with is, let's say, right, we have our matrix and we have our I hat x and I hat y, and then we have our j hat x and our j hat y. So we have our basis vectors. So that should all make perfect sense so far. With me so far?
Yep. Other than you normally choose the I basis vector in red, but yes, I get it. And some colors.
am I changing colors?
It's minor and it's totally
sure?
arbitrary.
I'm going to disagree.
Not even anymore. Nope, I'm wrong. In that case, you definitely use red. I don't know. Okay, I'm super wrong. I'm the wrongest. Okay, never mind. Proceed.
Color's important. The aesthetics of this presentation is just impeccable. Anyway, so one way to think about it is we're going to augment our matrix, and we're going to add. I don't know if there's. I have a quick scan through the Wikipedia page and see if they use a common thing. No, they don't. All right, so I'm going to get to call this translation X and translation Y. So this is like the simple way to represent it, and it's basically do the matrix transformation and then just add on that. So you could imagine that we'd have a matrix that's like 1 1 neg 1 1 like before, and then like we'll shift it over 5 5. And so you can imagine what that would do is we'd start with our basis vectors there and there. Make them pretty, and then so that's just the thing, and then we'd add on 5 and 5. Let's actually make that a bit different. Let's make that 5 and 1. So we'll go across 1 2 3 4 5 and 1 up, and so suddenly, and this is where it gets a little bit weird, is our basis vectors are actually here and here, because we've translated everything. And so you can imagine then if we have a vector that's like that on sort of in the starting world, and we're going to use orange for where it ends up, it's going to end up here once we apply this matrix, but actually it's not going to end up there, it's going to end up there because we've translated it. And so the final vector will be that.
And it's not linear anymore because we no longer have the origin always in the same place. Is that why? Well, I guess the origin technically is in the same place. We're just representing it somewhere else because we've moved it.
Yeah, so this is getting into like what the mathematicians would call it, and I think you're right. I think this is no longer technically a linear transformation. It's an affine transformation. So if you were thinking like set theory style, like an affine transformation, if that was 0 and 0, would be a linear transformation. So all linear transformations are affine transformations, but not all affine transformations are linear transformations. Make sense?
Yeah, I mean, I just Googled I did the Google definition, didn't help me either. So it's basically a label. It's not. There's nothing too intuitive about the name of it. It's just a label.
Yeah. So
it says from Latin. It means connected with, which doesn't really help.
Mm-hmm.
But okay, that makes sense. Basically, you're preserving the value. You're preserving everything except you're moving where it begins. You're moving the.
Yeah.
Well, you're translating it. I mean, we understand that.
Simple as that.
Yeah. That's all it is.
Okay, so let's talk about how we can represent this.
Yeah, we're almost out of time, so just in case.
Okay, are you? Do you need?
No,
to,
I'm good. I'm good. I'm just doing the 1 hour warning. That's all.
That's okay. I think we've got enough time to get this done into code. So, what you'll find is if you. I'm just going to shortcut this because I know how it works and it's sort of easy to explain. But let's say you have this situation and you're like, right, well, I want to add on, I'm not on the right layer. Yeah, let's do it this way. So if we were like, x, y, and we wanted to do I, x, I, y, j, x, j, y, t, x, t, y, that is equivalent to going x, y, I, x, I, y, j, all that stuff, plus t, x, t, y. And then you end up doing that thing where you're like, that times that, all that business, and then you add on that at the end. And this is the bit I'm shortcutting. I'm going to tell you just straight off the bat that that is equivalent to this: x, y, 1, I, x, I, y, j, x, basis vectors, j, y, t, x, t, y, 0, 0, 1. And strictly speaking, you don't even need that last row, but we kind of want it to end up with, x dash, y dash 1. And if I'd left off this last row, it would end up being a 2D vector without the 1 on the end. But sort of for congruence, you sort of include it. It depends whether you want to return a v3 or a v2. But hopefully
but you have no information in the v3. You've just got the identity in the v3 because you're not actually using it, right?
Sorry, that's really confusing. What I'm saying is, if I were to go ahead and do this, blah, I'd end up with that. Because you'll notice that it's a it's a 1 by 3 and a 3 by 2. Sorry, is that right?
2 by 3. I think it's 2 by 3. 2 across and 3 down.
I'm going to confuse myself even worse.
It's 2 by 3, so the end result should be 2
yeah. By... maybe it doesn't work like that. Okay, never mind. Anyway, suffice to say that this is right. This is correct. I can tell you for sure this is correct. So what I was going to say is basically when you're storing this thing, if you're storing an affine transformation, you just need to store 6 numbers. You don't need to store that, because that's always going to be the same.
Yeah, that's what I kind of was trying to allude to, the fact that it's not holding any information, because it's actually just the identity part of a 3 by 3, but you've shoved real information into the 2 by 2 part of it.
Exactly. So the way this works, let me just draw out the way this works, is now we have a 3D vector. It's got 3 dimensions, and we have a 3D dimension output and a 3 by 3 matrix. So we're working in 3D now. So if this is our sort of ground plane, and here's our origin, and we've got x is coming out there, and say maybe our x and y, I hat and j hat are just the identity, but we're doing a translation, so we have like 1 0 0 1 3 3 or something, if that's our augmented matrix. What we have there is this vector here is, I'm going to draw it in pink, is coming up out of the surface on the z-axis 1 unit. Okay?
Yep.
And if we look at our basis vector, 1 unit on the z is tx and ty. So we've gone 3, 1, 2, 3, 1, 2, 3, and we've come up 1. So that's that there. That's really not. I'll draw it like that but strictly speaking, it's a vector coming out of the origin. Like that is our basis vector, ijk. So that's k hat.
Right.
So if we have 1 there, we end up adding this 3, 3 basically. We end up to whatever we have. So say we have a vector there, we apply some operation to it, and then add on that basis vector. So 1 times that, we do that, and it's sitting up there. So that's how we get a translation, is we're basically operating on a plane that is 1 higher, and then obviously the final result ends up with this 1. And so where that 1 comes from is because nothing else is contributing, and this is always 1. This is always the identity. So we get 1 back. So we're ending up 1 unit above the sort of z equals 0 plane.
Mm-hmm.
And we applied this translation. So does that make sense, how I arrived at that?
Yeah, visually it just seems odd that we're using 3-dimensional space to resolve like what should be a simple transfer, like sliding I hat and J hat up to the corner there. But you have this extra 3-dimensional information that I'm not sure how it's contributing to the answer in 2-dimensional space.
So basically this is our k hat basis vector, and we're always, because we're by definition always going to put 1 on the z-axis, like the input to this is always going to be 1. You're always going to get 1 times k hat basically.
Mm-hmm.
And so that's sort of how you say, right, well, I just want to add these two. So it ends up being, plus 1 k hat, because it's like x I hat plus y j hat plus 1 times k hat.
Right.
And so you'll have recognized this from before. This is the same, this is the business we're doing there, having x times I hat, y times j hat, plus 1 times this t vector, which is, t equals k hat, ignoring the fact that there's actually we've stuck a 1 on the end.
Mm-hmm.
So you with me so far?
Yeah, barely. Like I get what you're saying, but to me, like, I don't like the answer, so-called visually, for this in 2-dimensional space is the pink arrow. It's just how the blue arrow is relevant at all.
Okay, so the blue arrow in this diagram is k hat.
Right, but why do I care about k hat?
So the reason you care about
2D hipster, so I don't know.
So what happens is when you go to draw, you've done all this maths, you don't care where this came from. This got injected for you. So you've only passed in that, and then once you get a vector at the end, you don't care about this anyway. You just take that. So
right, but I'm trying to, from a fundamental understanding, I'm trying to figure out why, how the blue arrow contributed to the answer, so to speak. Like, and I know that's what you're explaining, is how k hat is derived. And
so I'll draw now we've covered all that. I'll draw that a little nicer. Let's do that.
I mean, I totally get how we're getting k hat. That's not the problem.
Yeah.
Like,
so I'm going to draw. This is our nice big plane now. This mostly looks good. So this is our origin. And we have, this is going to be x hat, and this is going to be y hat. And for the sake of this, we're just going to say, j hat equals y hat and x hat equals I hat. So we're not actually doing any linear transformation here. We're not doing any rotations or anything.
Yep.
We're just going to translate. So what we're going to do is we're going to say, let's pick a vector in this space. Let's say it's that. I'm going to go down. Yeah, I'm going to go down again. So this is still sitting flat on this plane.
Yeah, right.
So this is going to be vector v. And now we want to translate it. So what we're going to do is we're going to pick, we're going to say our translation vector, and I was going to draw it in blue, t equals, let's say 3 on the x-axis, 1 on the y-axis. So already we can predict, 1 on the y-axis, so it's going to come up 1, it's going to go 1, 2, 3, it's going to end up somewhere around here. Just if we were just adding t onto v. But we want to do this in a way that we can use a matrix. So what we're going to do is we're going to define k hat as 3, 1, 1. So now we have k hat, and let's draw that up here. So we're going to say it's 1 up, and it's 1, 3 on the x-axis. So 1, 2, 3, and 1 on the y-axis. So we've ended up here. And so then, like, if we draw like the shadow of that vector, it's like it goes back down onto the plane there. So hopefully you can see that this is like sitting off the plane 1 unit up on the z-axis.
That makes sense.
So we're up here. Okay, so now we want to apply this transformation. So we have this I and j hat are the same, but k hat's different. So 1, 0, 0, 1, 3, 1. And we could do it like that, or we could say 1, 0, 0, 0. So we extended this to a 3 by 3 matrix.
Yep.
And this vector here is this blue vector. It's our basis vector. So what we've done is we've taken this v and we've gone, we'll have sum of the x. So that's, that's still exactly the same. And sum of the y. So we've already got out to here just with those two. And then we add on, so we've got that times vx plus that times vy plus this times vz. Now now we're sitting on the plane, and if that's 0, that equals 0. We don't get anything out. So what we need to do is we need to sort of define the fact that we're going to bring our vector up by 1 unit. And by bringing it up by 1 unit, we want 1 times that.
I get it now.
Yep.
Yeah.
Why?
You're bringing this all up 1 unit just basically so that you can, like you literally said at the beginning, so that you can use a matrix to get to the same spot that you would have done with vector addition.
Yes. And so then we end up with, that ends up being, so we have 1 unit of z, and we know that, with our new basis vector of z, it goes out in 3 dimensions up to here. So, and it ends up being
the same spot, except for 1 node.
We basically translated it, and then once we're done, we can we can just ignore that and bring that back down onto the plane, because we don't need that extra z-axis. So that's how that works. And
Cool.
the reason that we do this is now we have a matrix. And because we
Right.
have a matrix, we can go blah, 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 times blah, 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 and end up with like a single matrix that does, you know, a rotation and a scale and a translate. So we can do that thing we were talking about before where it's like, where was it? This business here. So, you know, you recall that, like, say, layer, this was our origin, and we wanted to like move everything around so it's there. So we need a translation there. And by the same token, you know, if this is a thing in model space, we're moving it from, you know, the origin out to here to get our dude to appear there. So we need a translation, which is why the you know XNA dot matrix is a 4x4 matrix, because it does the same thing in 3 dimensions. So you've got you know, you've got the X, so I hat, J hat, K hat, which is actually now like the, I've lost my pen. You know, this a legitimate 3D transformation. So this is like a linear component, and then you've got this bit here.
Yeah. There's L hat, and then there's like 0001 on the other end of that.
Yes,
so.
And I'll show you a nifty thing. If we come back over to X and A, we just matrix foo. I've already got a foo matrix 2. You'll notice that you can query the backwards, down, forwards, left, blah 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 translation. So if you ask for the translation, it gives you a vector 3, and that vector 3 is, you know, it gives you that. It slices off that.
Yeah, that's awesome.
So that's
the description in the IntelliSense actually nailed it. It was saying, give me back the position that's stored in this matrix. So you're literally pointing to where you stored this as a bonus.
And you'll notice that if we look at this, M41, M42, M43. So it's, you know, bottom row, 4th row, and the first 3 values.
Yeah, cool.
So that's how
actually understand something.
Excellent. Perfect. Well, that's how all of that works. Let's quickly
jam it in there.
Let's jam it in. I'm going to call it X and Y.
Okay.
And you'll notice that, you know, this handy little thing's fired off. It's like, right, well, all of these matrices you've got there don't actually work. So let's alt.x equals 0. That's fine. Y equals 0. So we know.
My little trick before of only declaring the 2 ones was good for the moment, but it wasn't good for the future when I have to change this code and I don't remember to put that value in, and then I get bugs. Whereas yours is like, you gotta reason about this before you can do it, or else you won't compile. So
exactly.
Very cool.
Okay.
Very cool.
So, oh yeah, and identity is obviously very simple as well. X
0, 0.
Y equals 0. Okay, so the first sort of interesting one is this transform, and I've already just slammed that in because we know that you know, a vector v is effectively you know, is v dot x and v dot y and 1. So we know we have 1 times the translation there and 1 times the translation there, and we know that it's just like 1. So for the transform, we can actually just get rid of it entirely. It's very straightforward. So hopefully that made sense.
Right. Yeah, we don't need it for yours. Yeah, sorry. I was trying to do this, but then I decided I wanted to follow what you were saying.
Oh,
so
yeah,
no, I'll do that.
That's fine.
I'll do that later.
Yeah.
I'll do that. Okay, so yeah, for us, we don't care about this or whatever. Yeah. Okay.
Yeah. So for the transform, that's really actually quite trivial.
Yeah, you just basically did vector addition, but inside your matrix object or your structure.
Now, for the this business here, now we have to go and think about what the matrix multiplication looks like. So we already know that we don't have this last row, so we're just going to ignore the fact that we have, r dot m 02 equals, well, that's not a thing because we're not storing it as we covered. But we do need r dot x and r dot y. Sorry, yeah, m2 0 and m2 1 as sort of the things that is. So right, so going I'm trying to think about how this works. Across and down. So for this one, we go across, and then we go across, and then we go down. So it's 0 times x. So that's fine. We've got that. And then this one is yeah, I'm pretty sure that this is actually going to be exactly the same because it's all zeros here.
Right.
Like, for example, this 1 0 would be across that times that plus that times that plus that times that. So 0 times x, yeah, across and down. So just to smash forward through the maths, I should have actually opened up my code for this to be absolutely sure. But so these last ones, let's work these out. So this is across, so, and down. So we are x a dot x times b dot m 0 plus a dot y times b dot m 1. No, cross and down. So m 10. And then across is a dot this one, which is 1, times b dot x. So we've come down there, that one, that one, that one, 0, 1, 0, x, and then across on the a's, so a dot x, a dot y, and 1. So that looks pretty good to me.
Yeah. No, I mean, it's easier when I'm looking at the sets, but this it's just trying to follow the cursor. And this is kind of,
so
I mean, I know I could do it if I sat here and
if you really want to, like, if you want to be as good as me, like sitting there for like a minute, is that right? Is that right? You know, what you could do is after this, you can just go and just delete that and try and work out the maths exactly on paper or whatever. But by the same,
it's sort of a rote thing though. It's not really conceptual, like understanding it versus oh darn it, where's cell 1 versus cell, but no, I probably should. It's probably the right thing.
It's not a bad thing just to do once, just for funsies, because if you're doing a lot of sort of game programming, you actually, like, maybe you need a different transformation type. Maybe you need a 2x2. Maybe you need an affine. Let's, maybe we change this to, I like to call mine form 2D.
I've seen this before too. I think other engines do the same thing, or maybe I'm just so used to Pixel 3D.
Yeah, well, this is fairly common, and I'll show you a link later. So anyway, I was going to finish off this one. So there's AX times, we're going down this one now. Yeah, so that would be M01 and M11 and BY. And already you can sort of see how this works. So we're doing like a transform here.
Yeah, and then I do see it.
And then at the very end we're adding on the second. Sorry, we're transforming the first translation, but then at the very end we're adding on this second translation. So this business here should look very similar to what we have here. We're just adding on the transform at the very end. So
yeah, can you go back to the transform method of our transform 2D?
Yeah.
Because I don't think I
did something wrong here. You just didn't finish that.
Yeah, I didn't. Oops. Yeah, I didn't do the thing. It's not called.
That's all right. So, so hopefully that should all make sense. So once you've finished that, we'll bang it into the thing, and we'll just try and make sure everything works, and try and do.
I think that's right.
Looks pretty good to me. So good. What we want to do is we want to try this business here and see, if we apply these to our lines, do we get the result we expect? So let's. Right. We need to make one more of these things. So we'll grab we'll copy scale and turn that into create translate.
Oh, right.
And so X and Y.
First, I'm gonna just do magic here. I wasn't going as fast as before, so I just need to.
That's all right. Take your time.
Well, no, we're already over, so.
That's fine.
What's 2 more minutes? Yeah, so we'll do this. And then now I'll copy it to create transform. Sorry, create translation. But here's a part where wouldn't I want integers here for translate? Well, I guess it doesn't for this.
No, for this one, for this, you might want to translate by a floating point amount. So that's fine. But yeah, like I was saying, is if you maybe wanted say an integer matrix or a rational matrix, I think we mentioned last week, and or if you wanted a fixed point one, then you'd use those, but you'd use them throughout. Okay, right. and okay. So and maybe you want to overload that at some point and be like vector 2.
Right.
Something. But for the time being, we'll just stick that in.
Yeah.
Let's go all the way up to the top, and this is going to be really simple. Let's change the scale matrix. Create translate, and we know that this is 50. Actually, I might go 200 here. And so it's a bit hard to see, but obviously they're not overlapping because, as we were saying, it's not commutative or whichever. I should probably look that up.
Associative, commutative, there's a bunch of them. I don't remember exactly which one's what. Did you get rid of your scale one, or is I just? I
replaced the scale with the translate. Associative. Yeah, we can read the Wikipedia page and find out exactly the terminology later, but Anyway, we know.
I remember there's a really good Khan Academy video on those qualities that vaguely remember.
It's the sort of thing I have to look up every time. I'm like, which one is it?
They're just labels. I think, but I understand what the label is for, so that's good.
Okay, so and hopefully you're happy with how that works. And I mean, we could maybe we could change this, just comment out those ones and make new ones. If we went create scale 1,2. I think 2 is probably going to work. Let's see if they actually appear on screen. Y is probably the wrong one. Let's scale 1, 2, 1, and it might actually appear on screen. So the animated one was pretty, but like this should give you a better idea about, you know, if you translate first, you get, you know, that translation then gets scaled, whereas if you translate second, you know, it doesn't get scaled. Blue is bar, yeah.
Right. Yeah, that makes sense.
Yeah, so we've scaled the translation, and that should make a lot of sense with, you know, what we did here, which is, you know, we're applying. If we do it in that order A, B, we're applying. We're doing a transform to the translation of the A vector, whereas if we do the translation second, you know, we're just slapping it on the end. So hopefully that all makes good sense.
It makes sense. The only thing I'm confused about is, I mean, obviously the results are different, but you know, to say that they both did not receive the scale, to me, when I know that they are the same size, kind of weirds me out.
Are they the same?
You know what I mean? Are they not? It seems like
no. They should be the same. Whoa, yeah, no, I think they should be the same size because we're.
I mean, like they're like visually of the same length, even though the scale would have been applied.
I am curious as to whether we have a bug or we're just seeing other things. Because what happens if we like bump that up to 4, and maybe we drop this down to like 50, 100, 150, 250. I think you have a good question there, and I'm just trying to think about the best way to actually go about demonstrating what's going on here.
Well, it's something we can, maybe I can ponder it and we can deal with it next time.
Because one is translated and then scaled that way. One is scaled. Yeah, I think it's fine. I think it's fine because if we don't translate that one, if we don't translate that one.
Maybe they actually are different lengths.
I want to say they're actually fine. Oh, it's 25 because it's. Well, I'll tell you what. I will go off and make sure we don't have a bug.
It's probably it's probably just my eyes might be tricking me because I know we're talking about small amounts of difference.
I know what you're talking about, and I have a feeling that we don't have a bug, and that the difference is actually the fact that like I think this is actually correct, and I'm just struggling to sort of explain why it's correct, because it's sort of a situation where that's sort of just how the maths works out. Yeah,
that's curious.
But
yeah, it's probably one of the, it's probably like the, like I said, for like unfortunate values that are uniform values or something.
Because what we can do to demonstrate this is foo is doing the transform first and then scaling up to the foo is doing the scale first and then the translation, and then bar is doing the translation and then the scale, so it does a translate. So because why it's confusing is we're doing like two steps at once. So if we just look at here is yellow is translate. Sorry, yellow is scale. So as you can see, that's going 100, and there's 1, 2, 3, 400. I think it's 100.
Oh, right, and the scale, but the scale is actually
and then we're doing a translation by 100 at the end. Okay, so we've got that. Scale. So if
I missed the 1 in the scale where the y component of the scale is 1. So you're not actually going to see a change in the rectangle visual, because you're not actually changing its volume.
Exactly. So yeah, this is fine. And so if you can see, if I just move the initial vector there, 0 scales there and then translates up there.
That's right.
100, 100, and then the reason I think just the reason it's confusing is because there's 2 steps involved, and you have to actually think about the 2 steps. We're not actually drawing 2 steps. So in this case, we're doing a translation by 100, so we end up there, and then we're scaling 1, 2, 3, 4 times bigger, and we're ending up here.
Mm-hmm.
And then obviously combining that all together, you get this, which if you don't think about it that way, that without the intermediary steps is actually quite confusing.
Right.
But obviously, like the reason that you do the code like this is to make it not confusing. It's like, I want to scale it, then I want to translate it, and then eventually you're just going to be like, that's my, that's going to be, that's my camera matrix, and I'll just pass that to everything and forget about it until something goes wrong and you have to go and debug it, which is why you need to know how it works. But the point is, now we have everything to actually do some sort of sensible camera. You remember, like on River City, at least in the editor, we had this thing where we could like pan the camera around and scale it and stuff, and
most we know,
and basically, like if you pan a camera, like you want to pan the camera that way, that's equivalent to just translating the world that way.
Right.
And same goes for scale and all that. So let's finish that off there. And now you have a nice new transformation matrix. So enjoy that one. And I'm going to find OBS and